Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from October-November 2023, Paper 4, Variant 1. As always we will discuss these questions in detail so you can improve your conceptual understanding of physics and also you can have better understanding of these exam questions. Let's study together, let's improve together. Question 1, Part A says, state what is indicated by direction of the gravitational field lying at a point in a gravitational field. In order to answer this question, first of all, we can simply imagine we have a beautiful planet and the mass of this planet is capital M. Or simply you can imagine any mass. So this mass will have its own gravitational field. So here we can draw some gravitational field lines. So these are gravitational field lines. These lines are directed inwards because gravitational force is attractive force. This question is simply asking us what this arrow is telling us. Imagine that we place a unit mass small m here. What is direction of force on this unit mass? This is to the right. So this is what is indicated by arrow on gravitational field lines. Actually, there is nothing around this one what we can see. This is just kind of abstract idea. We just imagine there is a field around this one. There is a region around this one. If we place any other mass, that mass will experience attractive force. This is just abstract imagination. This idea was given by Michael Faraday, and the same concept we use for charges. We imagine they have electric field around them, there is region around them. In that region, if we place charge will experience force. And in case of gravitational field, there is a region around the mass. If we place any other particle with mass in that region, it will experience attractive force. And these arrows we use to represent direction of force on that test mass. So that's all. This is what we need to understand. How we can write the answer? In order to write the answer for this question, simply we can say direction of the force. This arrow is representing direction of the force acting on a test mass placed at the point. So anywhere if you place test mass, let's say if we place test mass here, there will be attractive force on this one. So it will be in this direction. So this is what this arrow is representing. Second part says, explain with reference to gravitational field lines why the gravitational field near the surface of the earth is approximately constant for small changes in height. In order to answer this question, again we can imagine we have a lovely planet. So this is the planet, and we can also draw the gravitational field lines. So we can draw some gravitational field lines. So here we can draw again some gravitational field lines. So you can imagine these are gravitational field lines around this planet. So these are gravitational field lines. Now we will look at this field from different distance. Let's say if we are looking at this field from far away, we are looking from here and we are looking at this field just very close to the surface, we are looking from this distance. This observer, when he will see, let's say this is observer A and let's say this is observer B. Observer B is very close to the surface, so this observer will see gravitational field uniform. So he will see gravitational field like this, uniform gravitational field. Why he will see uniform gravitational field? Because value of G is constant. Uniform means that value of G is constant. So we can say uniform means that G is about constant. Value of G at this point, value of G here is about constant. This observer will see uniform field because G is equal to G capital M over R square. R is the distance from the center. So distance from the center. So this one is the radius, mean value of g at the surface. So this is value of g at the surface. Now if we go a little bit higher, we can rewrite again g nu. This is equal to g capital M over r plus h square. And if h is very small as compared with r, so simply we can rewrite this one. We can say this is equal to gm over r square. Mean approximately these values are the same. So from here we can say it means new value of g, this is about equal to gs, mean value of g at the surface. So this observer, he will see uniform gravitational field, but observer at a certain distance, at larger distance, means observer A will see non-uniform gravitational field, mean he will see value of g at this point different, at this point different. So for observer A, field is non-uniform, but for observer B, we can treat as a uniform gravitational field because h is very small as compared with capital R. So these are the points you need to understand. Now let me show you the answer. This question has 2 marks. How you can write down your answer. In your answer, you can talk about these points. You can say change in height is negligible compared with radius of Earth. So field lines are effectively parallel, mean the field is uniform. Part B says a large isolated uniform sphere has mass capital M and radius capital R. Point P lies on a straight line passing through the center of the sphere at a variable displacement x from the center as shown in figure 1.1. Variable displacement. So this is our initial position and this is our final. So this is direction of displacement. So very important one. So direction of displacement is to the right. Figure 1.2 shows the variation with x of the gravitational field g at point P due to the sphere for the values of x for which P is inside the sphere. The magnitude of the gravitational field at the surface of the sphere is y. For part B1, determine an expression for y in terms of capital M and capital R. Identify any other symbols that you use. So simply is asking you value of g at the surface of the planet, means at this point. So g simply we can write on this will be equal to capital G times the mass of the planet divided by the distance from the center of the planet. So this is the symbol we have used. So simply we need to say this is universal gravitational constant, or simply you can say G is gravitational constant. So this is gravitational constant. This question has 2 marks if you have written this expression and also you have stated capital G is a gravitational constant, you will get 2 marks. This is how gravitational field changes inside a sphere if the density of the sphere is uniform. So this is true for uniform density. So if the density is uniform, this is how gravitational field, means value of G will change inside any sphere. So rho has to be uniform. So uniform density. Second part says explain why at the surface of sphere G always has the opposite sign to x. So we need to understand value of G at the surface. So value of G means the force of attraction at the surface. So force of attraction is this way. And we have already discussed that x is the displacement and its direction is to the right. So that's the reason displacement and g means the direction of force of attraction, they are in opposite directions. So these are the points you need to say. You can simply say gravitational force is attractive force, so it acts towards the center of the sphere. So force and displacement, they are in opposite directions. So these 2 points you have to mention, and this question has 2 marks. Let me show you the answer, how you can write down your answer. So you can mention these 2 points. Gravitational force is attractive, so it acts toward the center of the sphere at any point. Force and displacement are in opposite directions. If you have mentioned these 2 points, you will get 2 marks. Third part says complete figure 1.2 to show the variation of G with x for values of x up to plus minus 3r, for which point P is outside the sphere. So outside the sphere is very important. In order to answer this question, the best way is, first of all, simply we can sketch the sphere. So this is the sphere, and value of G is given to us at this point. This is equal to 0, and value of G at the surface of the planet we have. So here value of G, this is equal to 1.0 y. Now we need to find out value of G outside the sphere. If the distance is equal to 2r, distance is equal to 3r. So first of all, we can write down G is equal to G capital M divided by R square, and this is equal to 1.0. We can also write down the general expression for this one. We can say G times capital M divided by R square, and R is the distance from the center of the sphere. So at distance R is equal to 2r, value of G will be 1/4, means 1 by 4, because 2 square 4, so this is 1 by 4 of y, or we can say this will be equal to 0.25y. And at distance R is equal to 3r, we can also write down value of G. This will be equal to 1 by 9 of y, or we can say 0.11y. Now we need to mark these points. So when distance is equal to 2r at this point, value of G is equal to 0.25. So here we have 0.5y, so it will be half of that, means 1 2 3 4 5, means at this point. And again this value is about half of this, so it means it will be around here. Now simply we need to connect these points. So we will connect these points. That will be the shape of the graph, and this will obey inverse square law. So you also need to understand this will obey inverse square law, because G is proportional to 1 over r square. So we can simply connect these points. Simply this is how you can connect the points. So this is how you can sketch. On this side, when 2r, so it is halfway, so we have 1 2 3 4 5, so it will be about here, little bit lower, so this is halfway, so it means this will be here, and again half, so this will be about here. So we can also connect these points. You can simply draw and you can sketch like this. So this is how this graph will look like. Now let me show you the better one, how you can sketch a better one. So this is how you can sketch a better one. So this one is better one. So let me clean this one. So this is how you can sketch. Now one thing, maybe some of you will be very confusing about this point. On this side G is positive, this is G is positive, mean Y is positive. This side G is negative, so why it is negative on this side, why it is positive on this side. So you can simply imagine, if we place a mass here, for example small m, what is direction of force on this one? So the force on this one is to the right, and by convention we take to the right is positive because the field is pointing to the right. So that's the reason this value of G is positive. And here if we place a mass here, force on this one will be to the left, and by convention to the left we take negative. That's the reason value of G is negative in this region. So that's the reason we have positive here, we have negative value of G here. Just direction. G is a vector quantity. I hope this video was helpful. If this video was helpful, please like and subscribe, because your encouragement is very important. And the solution of remaining questions I'll be uploading as soon as possible. Meantime, if you have any questions, please leave your questions in comments and I will try to answer as soon as possible. And if you're looking for extra resources, means more resources to improve your understanding of physics, please join Patreon, and the link for Patreon is in the description of this video. See you in next video. Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from October-November 2023, Paper 4, Variant 1. As always we will discuss these questions in detail so you can improve your conceptual understanding of physics, and also you can have better understanding of these exam questions. Let's study together, let's improve together. Question second, part A says, define specific heat capacity. So first of all, we need to understand specific heat capacity is a quantity. So you need to define quantity in terms of other quantities. So this is very important point. When you need to define quantity, you need to define quantity in terms of other quantities, and when you need to define a unit, you have to define in terms of other units. Now let's try to define specific heat capacity. So first of all, we can simply say Q is equal to mc delta T. From here you can see if m is the unit mass, so m is unit mass, so we can simply say if m is unit mass and delta T is the unit change in temperature, so this is unit change in temperature. So this is unit change in temperature, means temperature changes by 1 Kelvin or 1 degree Celsius. Then this C, this is the specific heat capacity. So this one is the specific heat capacity. So this specific heat capacity will be equal to the amount of thermal energy needed. So the amount of thermal energy needed to raise temperature of unit mass by unit change in temperature, that amount of thermal energy is specific heat capacity. So we have specific heat capacity. If you look at the beauty of the equation, we have specific heat capacity means if we have unit mass and we change temperature by 1 unit temperature change, how much energy we need? That is the specific heat capacity. Now if the mass is double, so amount of heat means the thermal energy needed, that will be double. And if we keep the mass same and we want double change in temperature, means 2 times, so the thermal energy we need to supply, that has to be 2 times. So this is how these things are linked together. So if you try to understand like this will help you to understand physics in a better way. So your way of thinking will be like a physicist, and physics itself is a way of thinking to explain the nature. Now let me explain you this one in a little bit different way. It's a beautiful concept. Imagine that this one is the unit mass. So I can simply say this is unit mass. We can also understand this one in this way. This is unit mass and we place temperature thermometer inside. So you can simply imagine this one is thermometer. So we place thermometer inside this one. So here we have the bulb of thermometer. So this is our thermometer we place inside this one. And let's say temperature of this on this thermometer is 21 degrees Celsius. And if we change this temperature from 20 to 21 degrees Celsius, so this is 20, if we change to 21, how much thermal energy we have to supply? That thermal energy is the specific heat capacity. So here we have the thermal energy, we can say this is Q. So how much thermal energy we need to supply? That Q will be equal to C. So this is how you need to understand physics, and this is how you can define specific heat capacity. Now let me show you the answer, how you can write down the answer. In your answer you can mention these points, and simply you can say the amount of thermal energy required per unit mass per unit change in temperature. If you write on this, you will get 2 marks. So this is what is specific heat capacity. When the mass is unit mass and we want unit change in temperature, so the amount of thermal energy we need to supply, that is specific heat capacity. Part B says an ideal gas of mass 0.35 kg is heated at a constant pressure of 2.0 times 10 to 5 pascals. So that its internal energy increases by 7,600 joules. During this process, the volume of the gas increases from 0.038 cubic meters to 0.063 cubic meters, and temperature increases by 56 degrees Celsius. Show that the magnitude of the work done on the gas is 5,000 joules. For this question, first thing we need to understand, it is given to us that pressure is constant. During this process, pressure is constant. So simply we can use for this question W is equal to P times delta V. And also you need to understand in this case, as volume is increasing, so it means work is done by gas. So in this case, work is done by gas. So this is very important one you need to understand. You can also simply imagine this one. We have this cylinder, and inside this cylinder we have the gas. So this is our initial volume, then gas expanded to this volume. So this is V final. So gas is expanding, so it means work is done by gas. So work is done by gas. So how we can calculate the magnitude? So we have value of P, that is given to us 2.0 times 10 to 5 pascals, and we have the final volume, that is 0.063 minus we have 0.038 meters cube. Now if we solve this one, we will get our final answer, that is equal to 5000 joules. So this is the final answer, and this is the work done by gas. So in this case, work done by gas is positive, and it's the same as work done on the gas. So the negative, so work done by gas, we can say work done by gas. Work done by gas is positive, so this is negative of work done on gas, negative. If question asks you to calculate work done on gas, simply not the magnitude, so the work done on gas in this case is negative because work is done by gas. So these are some important points you need to understand. Next time they can ask you about these concepts, so try to understand these things. Second part says explain whether the work done on the gas is positive or negative. We have already discussed this point, so let me little bit highlight and then we will answer this question. So here we have the cylinder. So first of all, it was given to us that initial volume is 0.038 and volume of the gas increases to 0.063. So it simply means that the gas is expanding, so the work is done by gas. And work done on gas, in this case work done on gas, this will be negative of work done by gas. So work done on gas is negative because in this case gas is expanding, so work is done by gas. If gas is compressed, so simply you can say from here work done on gas is positive if the gas is compressed. So this is one thing you can remember. And work done on gas is negative if gas expand. So we can say if gas expand. In this case gas is expanding, so work done by gas is, work done on gas is negative, work done by gas is positive. And so this is simply you need to write down. You can simply say work is done by gas as gas is expanding against external pressure, so work done on gas is negative. Third part says determine the magnitude of the thermal energy Q transferred to the gas. This is a typical question about first law of thermodynamics. So simply we can say delta U, this is equal to Q plus W, and W is the work done on gas. So this is work done on gas. Now let me explain you a little bit about this equation. So here we have change in internal energy, and this change in internal energy, this one will be positive if Q is positive. So if Q is positive means the change in internal energy 100% will be positive if Q is positive, if work done on gas is also positive. So the change in internal energy, that will be positive. But if Q is positive, W is negative, then we need to compare which one is bigger. Then we can explain the change in internal energy, it will be positive or negative. Now also let's try to understand when this change will be negative. Change in internal energy, this one will be negative if thermal energy release means Q is negative, means the thermal energy is released, we can simply say delta Q, means the thermal energy is taken away from the system. So delta U will be negative. And if work done on gas is also negative, it means 100% change in internal energy will be negative. But if one is positive, Q is positive, W is negative, it means you need to check which one is bigger. So the change in internal energy will be according to that one. Now for this question, so these are the points you need to understand. This is what's the meaning of this equation. Delta U is positive if thermal energy is added to the system and work is done on the system, means on the gas. On system here is gas, work is done on the gas. So these are few things very useful. Now for this question, it is given to us that internal energy increases by 7600 joules. We need to find out value of Q, but we have already discussed that work done on gas in this case is negative because gas is expanding. So here we have negative. So this one is negative. Now you can simply say, because this change is positive, so Q has to be positive. So Q has to be positive. So simply Q from here you can say this will be equal to 7600 plus 5000 joules. So the final answer is 12,600 joules. So this is how we can answer. So when you do question, try to understand what actually is happening and try to get feelings about that. When you start feeling, it means you started to learn physics, you started to understand physics. So the answer for this question is 12,600. We can also write down this one 12.6 kilojoules, but this is given in joules, so you have to write down 12,600. Question 4 says calculate the specific capacity of the gas for this process. Give a unit with your answer. Value of Q we have just calculated, that is equal to 12,600 joule, mean the amount of thermal energy supplied we have calculated, and rise in temperature, change in temperature is given to us, that is equal to 56 degrees Celsius, and we have the mass of the gas, that is equal to 0.35 kgs. Now we need to calculate value of C. Before we calculate value of C, means the specific heat capacity, one very important point you need to understand that change in temperature in degrees Celsius is equal to change in temperature in degree Kelvin. So this point is very important. Now we need to calculate C, so we can simply say this is equal to Q divided by M times delta T. So we have value of Q, that is 12,600 divided by 0.35, and here we have this is 56. So we can also say this is the same as 56 Kelvin because the change in temperature 56 degrees Celsius is equal to change in temperature of 56 Kelvin. So from here we will get our answer, that will be equal to 640 joules per kg per Kelvin. So this is better way to write on joules per kg per Kelvin. But you can also use degrees Celsius because change in temperature in degrees Celsius is equal to change in temperature in Kelvins. So you can also write on degrees Celsius, but it's better to write on Kelvin. So our final answer is 640 and the unit is joules per kg per Kelvin. So this is how you need to answer. Part C says the gas in B is now heated at constant volume rather than at constant pressure. The increase in internal energy of the gas is the same as in B. Use the first law of thermodynamics to explain whether the specific heat capacity of the gas for this process is less than, the same as, or greater than the answer in B4. So first of all, we need to understand in this case first law of thermodynamics, delta U is equal to Q plus W. For the second process, volume is constant. So if volume is constant, it means that work done by gas, this one will be equal to 0. So it simply means that in this case, the change in internal energy, this is equal to amount of thermal energy supplied. And change in internal energy we have calculated, that was given to us in the question, and the value was equal to 5,600 joules. So new value of Q, we can say the new value of Q, this is equal to 5,600 joules. In the last part, in part B, we have calculated old value of Q, that was equal to 12,600 joules. So the value of Q new in this case is less than the previous value of Q, or we can say Q old. So from here we can write down now C is equal to Q over M times delta T. Same mass, same rise in temperature. So if Q decrease, it means that C will decrease. So the value of C will be lower. So this is how we can answer. Because in this question, in the second part, first thing we can understand, for the last part we have already discussed, the volume increases, so there is a work done by gas. So this is the first case, volume increases. But in this part, volume is fixed, so no work is done by gas. As no work is done by gas, so all the thermal energy supplied is used to increase the internal energy of the gas. So less thermal energy is needed. If work is done by gas, more thermal energy is needed. If work is not done by gas, less thermal energy is needed for the same change in temperature and also same change in internal energy. So these are very important points you need to understand like this, not just try to memorize the answer of this question. Try to understand what actually is happening, the conceptual understanding. I hope this makes sense to you. Now let me show you how you can write down your answer. In the answer you can mention these points. You can say same gain in internal energy, so same rise in temperature. No change in volume, so no work is done. As no work is done, so less thermal energy is needed for the same temperature change, hence lower specific heat capacity. So this is how we need to answer. So these 2 points are very important. So here work is. So let's try to understand a little bit in a different way. Let's say this is case 1 and let's say this is case 2, and here we can draw another one. So in this case gas is compressed. So let's say we have here, then we compress this one and the new volume has decreased. So this is kind of exercise for you. Now can you try to answer in which case the amount of thermal energy supplied has to be the greatest for the same rise in temperature, for the same rise in internal energy. If this is same, so which one is greater? So this is second, this is third. So which one is greater? Is Q1 is greater? Is Q2 is greater? Or Q3 is greater? Q1, here we have Q2 and here we have Q3. So which one is the greatest? Very good exercise. Now first of all, if you look at this case, case 1, the amount of thermal energy supplied has to be greatest in which case? So I hope you say in case 1 it has to be greatest because work done is negative. So we can rewrite here Q plus W, this is equal to delta U. If this one is negative, this has to be positive and its value has to be greater. So it means in this case highest amount of thermal energy needed for the same rise in temperature. So we can say Q1 has to be the greatest. How about the second one? Second one has to be this one. So we can write down the second case. If W is equal to 0, it means delta U is equal to Q. So it means this one has to be the second one. And this is third one because if W is positive, this is also positive. So for the same rise in internal energy, it means Q has to be lower. So in this case Q1 has to be greater than Q2 and Q2 has to be greater than Q3. Very important concept. Try to understand this one. If still it is not clear to you and if you have any questions, please leave your questions in comments. And if these videos are helping you and they are helping you to improve your understanding, please like and subscribe because your encouragement is very important. If you are looking for detailed notes, well written notes with specifications and also worksheets with detailed solution, join Patreon on Patreon, you will find these resources. Question 3 part A says the product PV for an ideal gas is given by this equation. P is the pressure of the gas and V is the volume of the gas. State the meaning of the symbols capital N, small m and mean square speed in this equation. So what N is representing? N is representing number of molecules of the gas, and m is the mass of single molecule, and this is mean square speed of molecules. So very basic question. So simply you need to write down the names, what n is representing, what m is representing, and what mean square speed is representing. This symbol is representing. This symbol is mean square speed. So in your answer, simply you just need to write down number of molecules of the gas, mass of one molecule of the gas, mean square speed of molecules. Second part says use the equation of state for an ideal gas to show that average translational kinetic energy of a molecule of the gas at thermodynamic temperature is given by this equation. So first of all, we have to use equation of state for an ideal gas. So we have to start with PV equal to nRT. In the final equation, we don't need gas constant, so simply we can write down this in different form. PV is equal to N times K times T. So we can use the second form of this. So we can write down PV, this is equal to N times K times T. At the beginning of the question, it is given to us that PV is equal to this, and you can also find this one in the data. In the given equation, this is also given. So simply we can replace PV with 1 by 3 N times M times mean square speed. This is equal to N times K times T. N is common, so we can simply cancel. So here we have M times mean square speed. This will be equal to 3 times K T. This has to be kinetic energy, so we can divide both sides by 2. So this one is kinetic energy of average kinetic energy of a molecule, and this is equal to 3 by 2 K times T. This is what we need to prove. Very common question and also very straightforward one. If you understand, PV is equal to this and PV is equal to NKT. Part B says the surface of a star consists mainly of gas that may be assumed to be ideal. The molecules of the gas have a root mean square speed of 9,300 meters per second. The mass of a molecule of the gas is equal to this. Determine to 3 significant figures the temperature of the surface of the star. Now it is given to us the surface has gas, is mainly made of gas. So simply we need to determine the temperature of gas, and this gas is ideal. We can assume this gas is ideal. So for ideal gas, simply we can say EK, this is equal to 3 by 2 K times T, and EK is the average kinetic energy of each molecule. So we can say this is 1 by 2 M times mean square speed, and this is equal to 3 by 2 K times T. From here we can cancel 1 by 2, so we will get T, this is equal to M times mean square speed divided by 3 times K. Now simply we need to plug in values. We have value of mass, that is 3.34 times 10 to minus 27 kgs. We need to be careful with units, and this is root mean square speed. So it means that if we have the mean square speed, you take root of that is given to you, and that is 9,300 meters per second. Now if we take square of this one, we will get mean square speed, that will be equal to 9,300. So this will be meter square second square per second square. Now simply we can plug in here. So this is square divided by, we have 3 times Boltzmann constant, that is 1.38 times 10 to minus 23, and if we solve this one, we will get 6,980 Kelvin. So this is up to 3 SF. So we can say this is 6,980 Kelvin, and this is up to 3 SF. So you can also write this is 6.98 times 10 to 3 Kelvin. So this is up to 3 SF. Part C says the radiant flux intensity of the radiation from the star in B is 2.52 times 10 to minus 18 watts per square meter. When observed at a distance of 4.16 times 10 to 16 meters from the star. Calculate the luminosity of the star. Give a unit with your answer. So first of all, for this question, it is given to us. You can simply imagine we have a star here. So this one is the star. And if we look at a distance of, as it is given in the question, so we can move over star to the center. So imagine that star is here. At this point, flux intensity is given to us. So at this point we have value of F, that is 2.52 times 10 to minus 8 watts per square meter. And the distance we have, this distance is also given to us. Value of T is given to us. And we need to find out what is the luminosity of the star. Means the power of the star, the emitted power of the star. We have to find out. So for that purpose, simply we can say F is equal to the luminosity of the star divided by 4 pi d square. We need to find out L in this case, so we can write down L is equal to F times 4 pi times d square. Now simply we need to plug in these values. We have value of F, that is equal to 2.52 times 10 to minus 8 multiplied by 4 pi times d square, and value of d is 4.16 times 10 to 16 meters, square of this value. Now if we solve, we will get value of L, that is equal to 5.48 times 10 to 26 watts. So this is our final answer. We can write on here 5.48 times 10 to 26, and the unit is watt, because luminosity is the power emitted by the star. So unit of power is watt. Second part says determine the radius of the star. So simply we need to use Stefan-Boltzmann law. And Stefan-Boltzmann law simply tells us that luminosity is equal to Stefan-Boltzmann constant times surface area of the star times T to the power of 4. So we can rewrite this one. So here we have sigma, this is constant, and surface area is 4 pi r square T to the power of 4. We need to find out value of R. We have value of L, that is 5.48 times 10 to 26, and sigma is constant and its value is 5.67 times 10 to minus 8. We have 4 pi, and here is R square, and value of T is 6980. We have just calculated. Now if we simply solve for R, we will get the radius of the star, and that is size of the star. So we will get 5.69 times 10 to 8 meters. So this is radius of the star. So this is how you can calculate. Part D says the gas at the surface of a star has a very high pressure. Use the basic assumptions of the kinetic theory to suggest why in practice a gas at the surface of a star is unlikely to behave as an ideal gas. So first of all, we need to understand condition for an ideal gas. So we can write down a gas is an ideal gas. So we can say a gas can behave as an ideal gas if no forces between molecules, negligible forces between molecules. If we write down here, negligible forces between molecules. So we can say negligible forces between molecules. This is condition for an ideal gas. Now if pressure is greater, it means molecules will be very close to each other, so there will be forces between molecules. So gas will not behave as an ideal gas at high pressure. And when a gas can behave as an ideal gas, if pressure is low and temperature is high temperature, gas can behave as an ideal gas. High temperature means molecules, they have higher kinetic energies, so they are away from each other. So in that case, volume of the molecule is negligible as compared with volume of the gas. So gases behave as an ideal gases at low pressure and high temperature. But if pressure is high, gases do not behave as an ideal gas. So this is the main point. I hope this is clear to you. Now let me show you how to write down the answer. In answer, you can just mention this point. You can say as pressure is very high, molecules are very close to each other, so forces between molecules are not negligible. Because this is condition for an ideal gas. If we treat any gas as an ideal gas, we assume that forces between molecules are negligible, and that is only possible if molecules are away from each other, mean the pressure is low and temperature is high. So these are the things you need to understand for ideal gases and also for this question. I hope this video was helpful. If this video was helpful, please like and subscribe. Like and subscribe because that is kind of encouragement for your teacher. And also, if you have any questions, please leave your questions in comments and I will try to answer as soon as possible. And if you're looking for well-written notes and worksheets with detailed solution and more resources, you can check Patreon. On Patreon, you will find all these resources. On Patreon, you can find resources for EdExcel, you can find resources for Cambridge A-level physics, IGCSE physics, and also for physics competitions like Physics Bowl, BPHO, and also Oxford University and Cambridge University admission test like PAT and ENGA. All these resources are on Patreon. So if you need them, you can join Patreon. I'll try to upload the remaining questions as soon as possible. See you in next video. Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from October-November 2023, Paper 4, Variant 1. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of physics and also you can have better understanding of these exam questions. Let's study together, let's improve together. Question 4 says, a heavy metal sphere of mass 0.81 kg is suspended from a string. The sphere is undergoing small oscillations from side to side as shown in figure 4.1. Mean this one is moving like this. So this is the oscillations of the sphere may be considered to be simple harmonic with amplitude 0.036 meters and period 3.0 seconds. For part A, state what is meant by simple harmonic motion. A typical question about simple harmonic motion, so you need to understand how to state simple harmonic motion. For simple harmonic motion, simply you need to understand condition for simple harmonic motion. Condition is A has to be equal to minus omega square x. Omega is angular frequency and this is constant, so we can say A is directly proportional to minus x. From here we can say A and x, they are directly proportional. So simply you can say A and x, they are directly proportional. X is the displacement. Directly proportional. So this is one thing you can say. A and x, they should be directly proportional to each other if motion is simple harmonic motion. So we can say this is one point. Now simply we need to state the significance of this minus sign. This minus sign is telling us opposite directions. Mean x and A, they have opposite directions. Mean when x is positive, A is negative. So let me write on here. When x is positive, it means A is negative. And when x is negative, it means A is positive. So this is significance of negative sign. So it means opposite direction. So we can say opposite direction. And if you write down these 2 points, you will get 2 marks. This question has 2 marks. So let me show you how you can write down your answer. In the answer, you can mention these points, these 2 points. You can say motion in which acceleration is directly proportional to displacement. So you will get 1 B mark, and the second one, acceleration is always in opposite direction to displacement. You will get second mark. Part B says calculate the angular frequency of oscillations. The time period is given to us and value of time period is 3.0 seconds. We need to calculate angular frequency. Angular frequency simply is equal to 2 pi, the angular displacement divided by time taken. So if this angular displacement is equal to 2 pi, this one has to be time period. If this is pi, this has to be t by 2. So let me explain you a little bit about this one. Angular frequency is equal to angular displacement over time taken. If angular displacement is equal to pi, so the time taken will be half of the period, t by 2. So again you will get this will be 2 pi divided by t. So this is the angle covered divided by time taken. So this is the main idea. Now simply we can plug in values. We have 2 pi, this is divided by 3.0. So if we solve this one, we will get 2.1 radians per second. So this is the final answer. Second part says calculate the total energy of oscillations. And total energy of oscillations, this can be equal to the maximum value of kinetic energy, or this can be equal to the maximum value of EPE, elastic potential energy, EPE max. The easiest way to calculate total energy is simply we can write down this is equal to kinetic energy maximum, and kinetic energy maximum is 1/2 mv max square. You no need to remember the formula. If you follow these steps, it's very straightforward. So 1/2, here we have m, and Vmax for simple harmonic motion is Vmax is equal to A times omega. So simply we can replace Vmax with A times omega. A is the amplitude of oscillations. Now simply if we simplify this, but we will get 1/2 m, and here we will get A square times omega square. Now simply we need to plug in values. Value of mass is given to us in the question, that is equal to 0.81 kgs. And value of amplitude is also given to us, that is equal to 0.036 meters, and value of omega we have just calculated, that was equal to 2.1 radians per second. Now if we simplify, we will get in this case 2.3 times 10 to minus 3 joules. So this is total energy of oscillations, mean the maximum energy. So this is total energy of oscillation, and total energy of oscillations is equal to maximum kinetic energy or EPE max, means when the kinetic energy is maximum, EPE this is equal to 0. You can also understand this one like this. Total energy, this is the sum of kinetic energy at any displacement and EPE. So when this one is maximum, this will be 0, and vice versa is also true. Part C says the suspended sphere is now lowered into water. The sphere is given a sideways displacement of 0.036 meters from its equilibrium position and is then released at time t is equal to 0. The water causes the motion of the sphere to be critically damped. On figure 4.2, sketch the variation of the displacement x of the sphere from its equilibrium position with time from t is equal to 0 to t is equal to 6.0 seconds. Now the key point is that we need to understand when oscillations are critically damped, what is the time taken? Time taken is about equal to one time period. About equal to one time period. So this is the key concept, is equal to about one time period. And in this case, we have already discussed that time period is equal to 3.0 seconds. And this is given to you in the question. Now, initial displacement is this. So it means it has to start from this point. And it will reach equilibrium position again when it is 3 seconds. So simply because it's time period, the time it will take to come back to equilibrium, that time taken is equal to 1 time period. Time taken to come back to equilibrium. It simply means that, let me explain you with one example. So imagine that this one is over pendulum. So this is pendulum and this is equilibrium position. We displace this one by displacement equal to 0.036. How long this will take to come from here to the equilibrium position? That time taken will be equal to 1 time period. So simply we need to sketch this one with decreasing gradient. So this is how you can sketch. After that, it will just stay here. So equilibrium. Then it has to be a horizontal line until here. So this is how you need to sketch. Let me show you the better one. If you want to look at a better one, so this one is a bit better. So this is how you need to sketch. So this is what question was asking us. Now let's try to understand a little bit more about this one. You can also look at these diagrams. So for better understanding, the green one, this one is critically damped. So this is critically damped. So you can see the time taken is about 1 time period. So this one you see 1 oscillation. So it takes about 1 time period to come back to equilibrium position. And if you look at over damping, so this is over damping. This curve is representing over damping. It takes very long time to come back to equilibrium, more than 1 time period. And you can also see the red one. This is light damping. So the red one, this is representing light damping. So these are some important points you need to understand about these 3 different types of damping. Question 5 part A says define electric potential at a point. And this question is also a typical question. You need to understand how to define electric potential. Electric potential, simply we can say, if I just write down here, electric potential. Electric potential simply is equal to the work done by external agent from infinity to a point. So simply we can say from infinity to a point per unit positive charge, per unit positive charge, unit positive charge. So this is how we can define electric potential. In fact, in physics, potential is not defined. What is defined in physics, that is potential difference. So that's the reason in this case we are also taking reference. So this is the potential difference between infinity and that point. So in physics, potential difference is defined, but potential is not defined. That's the reason we need to take a reference point. So it simply means that this is the amount of work done to bring a charge from infinity to a point. So we can also imagine this one. Imagine we have a charge Q and we place one little charge at infinity. So this is infinity. And we move this unit positive charge from this point to another point here. So the potential at this point is the amount of work done by external agent, because when we move this charge to the left, we have to apply force on this one to the left. So the work done by us is positive, and that work done per unit positive charge is the potential at this point. And so this is, we can imagine this one is the distance r. So this is, so if you move this charge from here to left, you have to do the positive work because you have to overcome repulsive force. And in this case, we also assume that initial velocity is 0. And when the charge reaches this point, final velocity is also 0. So we have to move this charge slowly. So the work done per unit positive charge to move charge from infinity to this point is the potential. So this is what is meant by potential. If this one is negative, so the work done has to be negative. So you have to move charge to the left, but you have to apply force to the right. So potential will be negative. because work done by us, that work done is negative, because displacement will be to the left and the force will be to the right, force applied by us. So the potential produced by negative charges is negative and potential produced by positive charges is positive. I hope this makes sense to you. If these videos are making sense and helping you to improve your understanding of physics, please like and subscribe and also share with your friends. Let me show you the answer, how you can write down your answer. In the answer, you can mention these points. You can simply say electric potential at a point is defined as the work done in bringing unit positive charge from infinity to the point. And if they ask you to define gravitational potential, so this is for potential. If they ask you to define gravitational potential, this is for electric potential. So if you need to define this one for gravitational potential, simply you need to replace. So gravitational potential will be equal to work done per unit mass from infinity to a point per unit mass. So simply you need to replace actually in this definition unit positive charge with unit mass. So simply this is what you need to replace. Rest is the same. Part B says two isolated charged metal spheres X and Y are situated near to each other in a vacuum with the centers a distance of 24 meters apart. Point P is at a variable distance x from the center of sphere X on the line joining the centers of the spheres. So it means this is sphere X. So here sphere X is located here. So we can say this is X and sphere Y is located here. So this is the first thing you can find out, because the distance is changing from the center of the sphere. So it means that at the center of sphere X, X is equal to 0. This is how you can figure out. So this is X and this is center of sphere Y. Figure 5.1 shows the variation with X of the electric potential due to the spheres at point P. So this is the net potential. This curve is representing the net potential. Now first of all we can draw the spheres. So at this point, so this is over sphere Y. We can also draw here, this one is sphere X. Now from here we can find out the radius. So the radius of this sphere is 4 and radius of this sphere is 2. The radius of sphere X is 2.0 centimeters, 2.0 meters actually, because this unit is meter. So you have to be careful with units. So this is meters. And radius of sphere Y, this is equal to 4.0 meters. And the second thing we can say, the potential of this one is negative. Potential of sphere X is negative. This one is negative. It means X has negative charge, or we can say this is negatively charged. So X has negative charge. You can conclude from here. Vy, as we see Vy, this potential is positive. So we can say Y has positive charge. So we can simply write down here Y has positive charge. So these 4 points are very easy to write down, but question is asking you simply 3 points, 3 conclusions. So if you write down these 4 conclusions, you will get 3 marks. One thing more we can also conclude from here, at this point potential is equal to 0. It means that, it simply means that potential due to X at this point is equal to potential due to Y. And potential is equal to K times Q divided by R. And here we have, this is also K times Q divided by R. In this case, R is the same because this is the distance from the center of X and also the distance from the center of Y. Distance is the same. So we can say R is the same. So R is the same. So we can simply cancel. R is the same. K is the same because this is constant. So it means the charge on X, the magnitude, is the same as the magnitude of charge on Y. So this is also we can conclude from this. I hope these points make sense to you. Now let me show you the final answer, how you can write down your answer. In your answer you can mention these points. 3 of them you need to write down, but if you write down more it's better. So these points we can mention. So we have here 5 points. Let's try to do a little bit more practice about potential against distance graph and electric field against distance graph. These two graphs are very common in A2 physics from electric field topic. So you need to understand how to convert potential into electric field and electric field into potential. So here we have electric field, let's say this is in newtons per coulomb, and we have distance, this is in meters. You need to sketch the graph. You can try this one by yourself and then you can compare your answer with my answer. Let me give you the hint. Electric field is equal to negative dV by dx. Now if you look at dV by dx from this graph, so dV by dx is simply equal to the gradient of the graph. So it means we just need to look at the gradient of the graph. If you look at the gradient of the graph, here you can see the gradient. Gradient is positive, but before this one, this gradient is 0. So it means initially electric field is 0. So it means electric field inside the sphere is 0. So we will draw just horizontal line here. So this is here. Now you see gradient is positive, but you have to take the negative of that. So electric field is negative. And you can see gradient is always positive, means from this point to this point gradient is, first of all, gradient is decreasing, so the electric field will be decreasing, then gradient is increasing, but it is still positive. So it means electric field is negative between these two spheres. We can also understand this one in a different way, because this sphere, it has negative charge, so this has negative charge. So if I look at any point, let's say if I look at this point, electric field due to this one will be to the left, because this is negatively charged sphere and this sphere is positively charged. So electric field due to this one here, this electric field will be also to the left. So this is, so electric field anywhere between these two spheres is always pointing to the left, and by convention we take to the left is negative. So electric field throughout has to be negative. Now let me show you the answer, how you can sketch. So this is how you can sketch. So this is how you need to sketch the electric field. So you can see inside electric field is 0. So inside any solid metal sphere or hollow metal sphere, electric field is 0. And for thin non-conducting shell, if the charge is uniformly distributed at the surface, still electric field inside is 0. So here electric field is maximum, but it is negative, so you can see it is negative. Here electric field is minimum here at this point, so you can see this is minimum, and then it is increasing again, but it is still negative. And inside sphere Y, electric field is also 0. So this is how you need to sketch. Very good practice. Try this question again by yourself. And if you have any questions, leave your questions in comments. Part C says a positively charged particle is placed at point P in B such that x is equal to 12 meters. The particle is released. Describe and explain the subsequent motion of the particle. Pretty straightforward question, but conceptual question, and also a beautiful question to test your understanding of this topic. How we can answer this question? First of all, we need to understand at this point what is direction of electric field. We have already discussed that sphere Y, this one is positively charged and this one is negatively charged. So this one is sphere X and then this one is negatively charged. So this one is positively charged, this one is negatively charged. So electric field due to positive, so this is our positive charge. So let me draw here. If we have a positive point charge, so this is positive charge, so the electric field will be pointing away from this one. So we are looking on this side. So electric field here, this is to the left. Electric field here, it will be upwards, and here it will be downwards at this point. And for the negative charge, so here we have negative charge, so this one is negative, so here we have negative charge. So if we draw the electric field due to negative charge, at this point it will be pointing to the left as well. So it means electric field here due to positive charge is to the left, and due to negative charge is also to the left. So this is direction of electric field. Now if we place positive charge at this point, positive charge, so positive charge will experience force in direction of electric field. So it means positive charge will just simply move this way. So this is direction of motion of positive charge. As in this case, along horizontal only electric force is acting. So electric force is the resultant force. And as resultant force is increasing, you can see the electric field. If we move this side, electric field is increasing. So it means that particle accelerate, but particle acceleration will increase. You can also understand this one from here. A is equal to F divided by M, and F is equal to EQ divided by M. Mass of particle is constant, charge on particle is constant. So if electric field is increasing, it means acceleration will increase. So few points you have to write down. First point, you will say particle will experience electric force to the left, and magnitude of electric force is increasing, so the acceleration of particle will increase and particle will move to the left. So these points simply you have to write down in your answer, and this question has 3 marks. If you write down these points, you will get 3 marks. So try to understand physics. Physics is something very beautiful. You need to feel the beauty of physics, beauty of thinking as a physicist. When you develop this way of thinking, you will see physics is very easy. So try to understand physics. And also please like and subscribe if these things are helping you. And if you need more help and you're looking for extra resources, please join Patreon. Now let me show you the answer, how you can write down the answer. This is how you can write down the answer, and in the answer you can mention these points. You can say particle is attracted to X and resultant force on particle is towards X. Particle accelerates and magnitude of acceleration is increasing. If you look at the last graph, when we sketch the graph between electric field and distance, you will see electric field at this point was maximum. So if we go this way, electric field is increasing, so it means that electric force is increasing. So this is how you need to answer. Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from October-November 2023, Paper 4, Variant 1. In today's lesson, we will focus on electromagnetism and alternating current. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of physics, and also you can have better understanding of these exam questions. Let's study together, let's improve together. Question 6, part A says, define magnetic flux density. So first of all, we need to understand magnetic flux density is a quantity. So we need to define this one in terms of other quantities. In order to define this one, first of all, we need to write down the equation that link magnetic flux density. So here we have B, magnetic flux density. So we can write down from here, B is equal to F divided by I times L times sine of theta. B can be defined in terms of F if I is unit current. So we can say if this one is unit current, and L if this one is unit length. So we can say unit length, and sine of theta, this is also 1. Sine of theta is equal to 1, and this is equal to 1 if theta is 90 degrees. So this is how we can define. So if all these quantities are equal to 1, then it means magnetic flux density in magnitude is equal to the force. So this is how you can define, and in the same way any unit you can also define. So this is the key concept you need to master. You don't need to remember all the definitions, but you need to understand how to define something. So this is the way how you can define any quantity or any units. Now let me show you the answer, how you can write down the answer. So this is how you can write down your final answer. In the final answer, you can say magnetic flux density is defined as the force. So this is equal, B is equal to the force if all of them they're equal to 1. Defined as the force acting per unit current per unit length on a wire placed at right angles to the magnetic field. Mean if the angle between L and B is 90 degrees, then that force is magnetic flux density. In magnitude, that will be equal to magnetic flux density. So this is the angle between B and L. So B and L. So this is how you can define. You need to understand the way to define, not just try to memorize without understanding. Part B says electrons are moving in a vacuum with speed 1.7 times 10 to 7 meters per second. The electrons enter a uniform magnetic field of flux density 4.8 milliteslas. Figure 6.1 shows the path of the electrons. The path of the electrons remains in the plane of the page. For part B1, state direction of the magnetic field. So in order to answer this question, we need to understand first of all, when electron is at this point, what is direction of the force? So simply we can draw direction of force at this point, because electron bend, it means direction of force at this point. This is in downward direction. So now we can draw here. So the force is down. So this is direction of the force on electron. And in this case, electron is moving. So here. So this is direction of motion of the electron. So simply we can say this is direction of motion of electron. For this one, we need to find out direction of magnetic field. So you need to understand, we need to use left hand rule. And Fleming left hand rule only is valid for conventional current, mean flow of positive charges. So you need to understand this is only valid for conventional current. So here, conventional current. Now in this case, if electrons are moving to the right, so what is direction of conventional current? That one has to be to the left. So we can draw again. So now we have direction of the force, that is down, and we have direction of conventional current, that is to the left. So what is direction of magnetic field? Now simply we have to use left hand. So first of all, we have direction of current. You need to understand this is FBI. So this is the force, this is magnetic field direction, and this is direction of conventional current. So we have force, so we can say force is down, and current in this case you need to understand. So if you move your finger, you can see here like this. Force is down and current is to the left, so the magnetic field is into the page. So in this case, magnetic field means the B, this is into the page. So this is how you can figure out. Simply you have to use your left hand. So we have direction of current, so you can use this finger first of all. So this is this way, and then you can rotate your hand. So here. You see, this is direction of current, mean this is to the left, and force is down. So this is direction of magnetic field. So this is pointing to the screen, mean this is into the page. So direction of magnetic field is into the page. This is how you need to figure. So this is how you can figure out. So simply you can say direction of magnetic field in this case is into the page. So simply we can write down here into the page. Second part says show that the magnitude of the force exerted on each electron by the magnetic field is equal to this. So simply we need to understand how we can calculate the force on moving charged particles. F is equal to BQV sine of theta, and theta is the angle between B and V. And in this case, angle between magnetic field and direction of motion of electron is 90 degrees. So simply we can say this is BQV, because sine of 90 is 1. Now simply we need to plug in values. Value of B is given to us, that was equal to 4.8 millitesla. So 4.8 times 10 to minus 3 teslas, and charge on single electron is 1.6 times 10 to minus 19 coulombs, and value of V is given, that is 1.7 times 10 to 7 meters per second. Now if we simplify this one, we will get 1.3 times 10 to minus 14 newtons. So this is the force on single electron. If electron has this much speed and it is in this magnetic field with this magnetic flux density. Third part says, on figure 6.1, draw an arrow to indicate direction of the centripetal acceleration of the electron where it enters the magnetic field at point X. We have already discussed at point X, the force, magnetic force on this particle is in downward direction, and this is the resultant force acting on the electron, and acceleration is also in direction of resultant force. So this is direction of centripetal acceleration at this point. So simply you need to draw this arrow. Part 4 says, use the information in B2 to calculate the distance d between the path of the electrons entering the magnetic field and path of electrons leaving it. Means value of this d we have to determine, and value of d in this case you can see this is equal to 2 times of radius of the circle. And radius of the circle we can calculate by using F is equal to mv squared divided by r, because this electron is doing circular motion in magnetic field. So we can use this one. And value of force already we have calculated in the last part, that was equal to 1.3 times 10 to minus 14 newtons. And mass of electron is 9.11 times 10 to minus 31 kgs. Then speed of electron is also given to us in the question, that was equal to 1.7 times 10 to 7 square of this one divided by r. So from here we can find out value of r. Value of r will be equal to 0.02 meters. So this is value of r. So the value of d will be equal to 2 times of this value, 0.02. So we will get 0.040 meters. So this is value of d, 0.040 meters. So this is how we can answer. Part C says the electrons in B are replaced with positrons that are moving with speed 3.4 times 10 to 7 meters per second along the same initial path as the electrons. The positrons enter the magnetic field at point X on figure 6.1. On figure 6.1, draw a line to show the path of the positrons through the magnetic field. So first of all we need to understand positron and electron, they have opposite charge and they have the same masses. As the charge is opposite, it means the force on positron will be in upward direction, so opposite to the force on electron. So it means positron will go upward, it will be deflected in upward direction. Now we need to look at the speed. This speed is 2 times of the speed of electron. So we can write on here r is equal to mv divided by pq. So if the speed is double, it means r will be double, because they are in the same magnetic field, they have the same charge, they have the same mass. So if v is double, so it means radius will be double. And this formula you can also derive. Magnetic force provides the centripetal force. So we can say bqv, this is equal to mv squared divided by r. So we can cancel this v with this v. So r will be equal to mv. So here we have mv divided by pq. So this is how you can derive this formula. This is very important one. You need to remember this one, and also you need to understand how to derive this. Now simply we need to sketch the path. So first of all we can look at this diameter of this one. This is about 0.9. So this diameter has to be double, 1.8. And the radius of this one will be 0.9. So this is about 0.9. Now simply we can sketch this. So positron will deflect somewhat like this. So this is how you need to sketch. So if you sketch this one for this question, you will get 3 marks. So this has 3 marks. Let me show you the better one. We can clear this one. So let me clear this one, and if you draw like this, it should be acceptable. You can simply sketch like this. Welcome to A-Level and EP Physics. In today's lesson, we will discuss past paper questions from October-November 2023, Paper 4, Variant 1. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of physics and also you can have better understanding of these exam questions. Let's study together, let's improve together. Question 7 says, a varying current I passes through a resistor of resistance capital R in the circuit as shown in figure 7.1. The current has magnitude 2I0 when it is in the positive direction and I0 when it is in the negative direction. The period of variation of current is capital T. Determine expression in terms of I0 and R for the power P dissipated in the resistor for the times when the current is in the negative direction and when current is in the positive direction. So simply we need to understand the power, because this is constant, current is constant, so power simply will be equal to I square times R, the same as we do for DC circuit. Now in this case value of I is given to us, that is I naught, so simply we will replace I with I naught, so this is I naught square times R. So this is how you can calculate power when current is in the negative direction. And for the positive direction, we have to repeat the same method. For DC current, we use I squared times R. But in this case, value of current is 2I0, so simply we have to replace I with 2I0 square times R. So if we solve this one, we will get 4I0 square times R. So this is how simply you can calculate. Part B says on figure 7.3 sketch the variation of P with time t between t is equal to 0 and t is equal to 2.0. Capital T means t is equal to 2 times of time periods. Label the power axis with an appropriate scale. So first of all we need to understand, for this part we have discussed that power is equal to I naught squared times R, and for this part power is equal to 4 times I naught square times R. So if we take this here 2 times I naught square, so this one has to be equal to 4 times I naught square times R. So this is how we can choose our scale. Now for this part, halfway, because this power is I naught square times R, so we can take 5 small square from here. So this is 1 2 3 4 5, and now simply we can draw a line. So simply we need to draw the line. From here we can draw this line here, and after the power is 4 I naught square, so we can draw the line here. And for this part again power is I naught square, so this is, you can draw this horizontal line here, and then we can draw the horizontal line here. So if you draw these 4 horizontal lines, you will get 3 marks. You can also connect them by dotted lines. Let me show you the better shape of this. You can also draw this one in a better way, so this looks a bit better. So we can also draw like this. Let's try to answer this extra question for your better understanding of alternating current. If you can handle this question, it means you have good understanding of alternating current. And questions about alternating current you will be able to answer. Pause the video, do question by yourself, and then come and compare your answer with my answer. For this question, it is given to us the variation with time of an alternating current in a resistor of 120 ohms is shown in the figure. What is the value of its RMS current? RMS current. And for part B, we need to calculate what is the mean power dissipated by the resistor. Mean power. So first of all, we need to calculate RMS value, IRMS. In order to calculate IRMS, first of all we will calculate mean square current. Mean square current. How we can calculate mean square current? So we will take this value here. So we will take the square of this value. So we have 4 here. So this is 4 square plus we will take this value. square of this value. So we will simply take square of this. We need to calculate mean square, so we have to divide this one by 2. So we can calculate mean square current, and if we solve this one, we will get 12.5 amps square. So how we can calculate IRMS? IRMS means that root mean square. So simply we have to take the root of this one. So we can write on here, we have mean square. If you take the root of this one, so this is root mean square, mean this is IRMS. Value of mean square we have, that is 12.5 amps square. Now simply we have to take the root of this. So if we take root of this, we will get about 3.54 amps. So this is value of IRMS. So this is value of IRMS. Part A we have answered. Now for the second part, you need to understand power, the mean power. Mean power has to be equal to I square times R. And now we need to understand, when we compare DC with AC, or we compare AC with DC. So let me write on you a very important concept, DC, and here we have AC. So if we compare these two, what value of AC we have to use? For example, here we have AC. If we go this way, we have to use RMS value. So this is the main thing. What we have to use? RMS value. So this is formula for DC. So if we want to use this one for AC, we have to use IRMS. So it has to be IRMS square, because this is for DC, this is for AC, times R. Now simply we can plug in values. We have 3.54 square of this value times we have 120, and if we solve, we will get about 1500 watts. So this is the main concept you need to understand, how AC and DC, they are comparable with each other. If we have AC current, how we can find the equivalent DC current for that? So you have to use RMS value. It simply means that all DC formulae, for example, if I need to calculate power, for example, power for DC is I square times R. How about power for AC? This is for DC. How about for AC? AC power will be equal to IRMS square times R. And if we write on for DC, for example, the power we have, this is V square times R. So how about for AC? Power will be equal to VRMS square by R, and so on. So how DC and AC, they are connected with each other? By RMS value. So this is importance of RMS value. I hope this makes sense, and look at this question again. If you have any questions, please leave your questions in comments, and if these videos are helping you, please like and subscribe, and also share with your friends. And if you're looking for more resources, you can also join Patreon. Part C says, use the answer in B to determine an expression in terms of I naught and capital R for the mean power in the resistor. So how do we calculate mean of something? In this case, we need to calculate mean power. So mean power simply will be equal to P1 plus P2 divided by 2. And value of P1 means when current was in the negative direction, we have already determined that was equal to I naught square times R. And when current is in the positive direction, we have calculated 4 times I naught square times R. And this is divided by 2. So simply we will get, in this case, 5 times I naught square divided by 2. So this is how you need to calculate mean power. Simply how to calculate mean. So this is our final answer. If you have got this answer, you will get 1 mark. Second part says, calculate the root mean square current I RMS in the resistor. We have already discussed that mean power for AC, this is equal to I RMS square times R, and value of mean power we have just calculated, so we can write down the value of mean power, that is equal to 5 by 2 times I naught square times R, and this is equal to IRMS square times R. So we can cancel this R with R, so we can rewrite here IRMS square, this will be equal to 5 by 2 I naught square. Now if we take square root on both sides, we will get IRMS, this will be equal to root of 5 by 2 times I naught. So this is value of IRMS. Very nice question. This question is a very nice question about AC, means alternating current. If once this question is not clear to you, watch this video again and try to understand concept, not just look at answers and try to memorize the answers. What you need to do, you have to look at this question again and make it clear that you have proper understanding of this question. If you have proper understanding of this question, a lot of questions about AC you can answer. If still not clear and you need help, you can leave your questions in comments. Question 8 part A says, show that the momentum P of a photon of electromagnetic radiation with wavelength lambda is given by P is equal to h over lambda. H is the Planck's constant. So how we can derive this formula? First of all, we need to understand energy of a photon. Energy of photon, this can be written as product of momentum and C. And energy of photon, we can also write down, this is equal to hc over lambda. So we can say this is equation 1 and this is the second equation. By comparing 1 and 2, we can write down Pc, this will be equal to hc over lambda. So C we can cancel from here, so it means P is equal to h divided by lambda. So this is how you can answer. So here we are comparing, you can simply say by comparing 1 and 2, by comparing 1 and 2, so by comparing 1 and 2, so this is the answer. Second part says, use the expression in A1 to show that a photon in free space that has a momentum of 9.5 times 10 to minus 28 Newton second is a photon of red light. In the last part, we have written that P is equal to h over lambda. Now we need to calculate value of lambda wavelength, so simply we can say h divided by P. And value of Planck's constant is 6.63 times 10 to minus 34 joules second. And this value you can find in the data given on the second page. You can find this value. And value of momentum is given to us, that is 9.5 times 10 to minus 28 Newton seconds. If we solve this one, we will get about 700 times 10 to minus 9. So we can say this is equal to 700 nanometers. And now if we compare this one with wavelength of visible light, wavelength of visible light is about 400 to 800 nanometers. So this one is red light. This is very close to this end, so this is the red light. So this is how you need to answer. Part B says, a beam of red light of intensity 160 watts per square meter is incident normally on a plane mirror, as shown in figure 8.1. The momentum of each photon in the beam is 9.5 times 10 to minus 28 Newton second. All of the light is reflected by the mirror in the opposite direction to its original path. The cross-sectional area of the beam is given to us. For part 1, we need to show that the number of photons incident on the mirror per unit time is 1.4 times 10 to 15 per second. I mean, these number of photons in 1 second, they are arriving this plane mirror. So how we can answer this question? For this question, intensity is given to us, so we can say we have intensity, and momentum is given to us, and cross-sectional area is also given. we have value of cross-sectional area. So how we can answer? So the best way to answer this question is we can start with intensity. I. Intensity is equal to power divided by cross-sectional area. And power we can write down, this is equal to the total energy over time times A. So intensity can be written in this form. And this is the total energy. And total energy we can write down N times energy of single photon. Energy of single photon. So let me rewrite this one here. So we can write down total energy of the beam will be equal to number of photons times energy of single photon. So here we can say this is energy of single photon and this is divided by T times A. And energy of single photon, as we discussed before, energy of single photon, this is equal to Hc divided by lambda. So this is energy of single photon. So we can replace energy of single photon with this. So we can say this is NHc divided by, we have lambda times T times A. As value of lambda we don't have, so we can rewrite this one. We can say momentum, this is equal to H over lambda. So from here we can say lambda will be equal to H over P, because we have value of momentum but we don't have value of wavelength. So we can replace this lambda. So we can rewrite this. So we have N times H times C, and here we have lambda, that is equal to H over P, and here we have time times A. So if we rearrange this one, we can say this is N times H times C times P, and this is divided by H times T times A. So here we have Planck's constant, so simply we can cancel this, and this is equal to intensity. But for this question we need to find out this N over T. So we need to find out N over T. So we can rearrange this. We can write down here I times A. This will be equal to N over T times, we have C times P. So we need N over T. So we can write here N over T. This will be equal to I times A divided by P times C. So value of intensity we have. This is value of intensity. So we can plug in values simply now. We have 160 watts per square meter, and value of A we have, that is 2.5. So we have 2.5 times 10 to minus 6 square meters divided by P, momentum of each photon. So we have momentum of each photon, that is 9.5 times 10 to minus 28, and C is a constant, its value is 3.0 times 10 to 8. Now simplify this one and you will get the final answer. If we simplify this one, we will get 1.4 times 10 to 15 photons per second. So this is our final answer, and this is what we need to show, that this is number of photons per second arriving the mirror. Very systematic approach, and this approach you need for many questions about quantum physics. So you need to understand how to use this. So in the exam, if they ask you something, you can start with this one and you can derive for that. For this question we have derived this one for number of photons per second, and in the exam they can ask you in a different way. Most of the time this is very handy, this is very important one. This one is very important. In many questions they will ask you about this one. For example, they will ask you if intensity remains constant and lambda increases. If lambda increases, so how about the number of photons? So if everything else is constant, so if lambda increase, it means n also increases, and vice versa is also true. So if lambda decrease, for example, it means n has to decrease. And this question is a very common question, in many past papers you will see about quantum physics. Second part says use the information in B1 to determine the pressure exerted by the light beam on the mirror, and pressure is equal to force over area, and force in this case is equal to rate of change of momentum. So we can say this is delta P over delta T multiplied by 1 over A, and momentum change in this case we need to understand. So this one is the mirror, so photon of light come, hit this one and go back with the same momentum. So in this case change in momentum is double because we have delta P. So if we say this momentum is P1, this momentum is P2, and we take to the left positive, so we will say P2 minus P1. So we can say P2 minus P1. This momentum is negative because we are taking to the left is positive, so it means momentum change in this case is equal to 2 times P. 2 times P. So this one is P, this is also P. Magnitude is the same. So we can write on here. So this is 2 times P over T times A. T times A. This is the pressure exerted by 1 photon. So this is pressure exerted by 1 photon. And what is the total pressure? So we can write on here now. Total pressure. So total pressure will be equal to pressure of 1 photon. So we have pressure exerted by 1 photon times number of photons. N is the number of photons. So we can little bit rearrange this one. We can say this is equal to 2P divided by A times we have delta N by delta T, number of photons in a given time here. Now simply we need to plug in values. We have 2, and the momentum value, we have momentum of photon, that was 9.5 times 10 to minus 28 divided by cross sectional area, that is given to us in the last part, 2.5 times 10 to minus 6, and number of photons per second we have already calculated, that was equal to 1.4 times 10 to 15. Now if we solve this one, we will get 1.1 times 10 to minus 6 pascals. So this is total pressure by the light beam. Total pressure by the light beam. So this is how you can calculate. So this is our final answer. So this is pressure exerted by 1 photon, and this is the total pressure exerted by all the photons. Part C says the beam of red light in B is now replaced with a beam of blue light of the same intensity. Intensity is the same. Suggest and explain whether the pressure exerted on the mirror by the beam of blue light is less than, the same as, or greater than the pressure exerted by the beam of red light. Nice question, and this question is based on part B. In part B we have already discussed that pressure is equal to 2 times P, this is the momentum, 2 times P over cross sectional area times we have discussed this is number of photons per unit time, delta N by delta T. In order to answer this question, so let me write down here, this is representing pressure and this is representing momentum. In this case intensity is the same. I can explain you this one with the help of this. I can simply say momentum increases because momentum is P, this is equal to E divided by C. As energy of each photon increases, it means momentum increases. So it means this one will increase, but number of photons will decrease. So it means pressure remains constant. In a simple language I can explain, but let's try to understand this one in more detail so you can have better idea. So what I have said is that if energy of each photon increase, so it means that momentum of each photon will increase. So if momentum of each photon increase, cross-sectional area is the same, so dN by dt will decrease. So it means momentum will remain same. So this is one way to explain. but maybe this explanation is not very clear. Now let me explain you this one in a better way. Intensity is the same. So intensity we have discussed. Intensity is equal to P over A. We have discussed this point already, and we can say this is equal to the total energy, E total, over T times A, and total energy we can say this is N times energy of single photon. So this is energy of single photon divided by T times A, and here we have the intensity. And energy of single photon, we can say energy of single photon, that is equal to momentum of the photon times C. So we can rewrite here. So we have N times P times C divided by T times A, and this is equal to intensity. From here we can say momentum, P is the momentum, that will be equal to I times T times A divided by N times C. So this is here momentum. Now we can replace this momentum with this value. You can write on here, this is 2, and we have I times T times A, and this is divided by N times C, and we have here this is N divided by T, and we have value of A here as well, so we can write down this is 1 over A. Now you can see here this N we can cancel with this N, then this T we can cancel with this T, and this A we can cancel with this A. So if intensity is the same, it means pressure is the same. I hope this makes better sense. So we can simply say, as in this case, intensity is the same, and this is just constant number, so it means pressure is also same. So this is how you can answer this question. I hope this makes sense. Now let me show you the answer, how you can write down your answer. In your answer, you can write down these points as I explained you with the help of this equation. So simply we can say photon have greater momentum. As energy of each photon increases, its momentum of each photon increases, but fewer photons per unit time. So this means delta n by delta t, this one decreases. Greater photon momentum but smaller number of photons per unit time, so pressure is the same. So this is how you can answer. I hope now you have better understanding why pressure is same when intensity is same. So next time you can understand, as long as intensity remains same, pressure remains same. Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from October-November 2023, Paper 4, Variant 1. In today's lesson, our main focus will be on nuclear physics and medical physics. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of these two topics, and also you can have better understanding of these exam questions. Let's study together, let's improve together. Question 9, part A says, state what is meant by nuclear fusion. Nuclear fusion simply means that when two lighter nuclei combine together and they form a heavier nucleus. This process of combining lighter nuclei to form a heavier nucleus is called nuclear fusion. And in this process, mass will be converted into energy. So a lot of energy will be releasing in this process. Let me explain you this one in a little bit better way. You can simply imagine we have this one nucleus and this is another nucleus. These two nuclei, they combine together, they form a heavier nucleus. Let's say mass of this nucleus is m, mass of this nucleus is m, and mass of this nucleus is capital M. And also in this process, energy will be released. And this energy release, this is equal to the mass difference between parent nuclei and daughter product. So we can simply say m plus m minus minus capital M. This is equal to delta M, and delta M is the mass defect, or we can say this is mass difference. You can also say this is mass deficit. So how we can calculate this energy released? So energy released, we can say delta E. This is equal to delta M times c square. So this is how we can calculate energy released, and this energy is equal to the mass difference times c square, mean how much mass has been converted into energy times c square. We can calculate energy released, and this energy will be released in form of kinetic energy of daughter products. So we can say daughter products plus gamma radiations. Simply you can say plus EM radiations. So this is how this energy will be released. It will be released in this form. So these are the points you need to understand about nuclear fusion. Now let me show you the answer, how you can write down your answer. In your answer you can mention these points. You can simply say is the process by which two lighter nuclei combine to form a single heavier nucleus while releasing massive amounts of energy. If you write on this one, you will get 2 marks. Part B says on figure 9.1, sketch the variation of binding energy per nucleon with nucleon number capital A for values of A between 1 and 250. This question is a typical question. You need to understand how to sketch binding energy per nucleon against nucleon number or mass number curve. And we also need to understand that iron 56, it has the highest value of binding energy per nucleon, Fe56. So it has maximum value, we can say maximum value of binding energy per nucleon. So this is one thing very important you need to understand. So that's the reason iron 56, this one is the most stable element. So this is most stable element, and that's the reason we have a lot of iron on our planet. So we have abundance of iron 56 because it's the most stable element. So we can also say we have abundance of iron because iron is the most stable element. Now keeping these points in our mind, we can sketch the curve. So simply we can start from here. So it will go sharply up and it will reach the peak, and after that it will go down. So iron 56 is located somewhere here. So we can say this is Fe56 because Fe56 is the most stable element. If the binding energy per nucleon is greater, it means element is more stable, not binding energy per nucleon. So you have to be very clear. Binding energy per nucleon, if this is greater, it means that element is stable, not binding energy. Binding energy not linked with stability. Binding energy per nucleon. Part C says on your line in figure 9.1, label a point X that could represent a nucleus that undergoes alpha decay. Most of the atoms with atomic number greater than 81, they undergo alpha decay. So simply we can say for alpha decay, atomic number if greater than 81, most of the element they decay by alpha decay. So simply we have to mark here. So we can mark round about here. So this point is point X. For the second part, we need to mark a point Y that could represent a nucleus that undergoes nuclear fusion. For nuclear fusion, we have already discussed lighter nuclei. They undergo nuclear fusion. So we can simply write down here lighter nuclei. So lighter nuclei you can simply mark here at the beginning of the curve. You can simply mark. So this point is Y. So this is how you need to mark these 2 points on this curve. Line mean curve. So this is curve. Part D says a nucleus capital Z undergoes nuclear fission to form strontium-93 and xenon-139 according to this equation. Table 9.1 shows the binding energies of these two daughter nuclei. The fission of 1 mole of Z releases 1.77 times 10 to 3 joules of energy. Determine the binding energy per nucleon in mega electron volts of Z. So simply we need to determine binding energy per nucleon of Z, and answer should be in mega electron volts. So how we can answer? So first thing you need to understand binding energy per nucleon. So this is what we need to determine for Z. So what do we need? So we need binding energy of one nucleus of Z, of one Z nucleus we can say. So we need binding energy of one Z nucleus. So we can say binding energy of one Z nucleus. So this is what we need, and we need to divide this one by total number of nucleons. So we can say we have to divide this one by number of nucleons. So this is what we need, divide by number of nucleons, and number of nucleons means is equal to the mass number, and mass number we can find out from here. So we have 1 here, so this is the mass number. So how we can find out value of this? So simply we can say in this case 1 plus mass number of Z, this has to be equal to 93 plus 139 plus 2. So we can find out mass number of Z, and mass number of Z in this case will be equal to 233. So this is the mass number of Z. So we can update here, we can write down here. So we have this one here. So this is the mass number. So we have determined the mass number. Now we need binding energy of one Z nucleus. But this energy is given to us for 1 mole. This is for 1 mole. This is energy released in 1 mole. Energy from one nucleus means how much energy will be released. So we can say energy released in 1 decay. We can say energy released in 1 decay, or you can say energy released when 1 nucleus decay. That energy simply we can find out 1.77 times 10 to 13 divided by number of nuclei of Z, and that is equal to 1 Avogadro's number because this is 1 mole. So simply you need to divide this one by 6.02 times 10 to 23. So if we solve this one, we will get 2.94 times 10 to minus 11 joules. So this much energy is released when 1 nucleus of Z decay. And for this question, we have the binding energy of nucleus. We also have binding energy of this nucleus. This is the energy released we have calculated. So how we can calculate the binding energy of Z? Binding energy. Before we answer this question, you need to understand when binding energy increase, it means energy is released. So let me write down here. If binding energy increase, it means that energy is released. So we can say delta E release. So this is one point you need to understand. Energy will be released, and if binding energy decrease, it means energy has to be absorbed. Or we can say another way to say this one is, we can also compare this one with mass. If delta M, or better way, let me compare this one. So we can say if the mass decrease, so we can say if the mass decrease, energy also will be released. So we can say delta E is released. So these two conditions are very important. You need to understand. If binding energy of products is greater than binding energy of reactants, means of parent nuclei, it means energy will be released. And if the binding energy of daughter nuclei is lower than binding energy of parent, it means energy has to be absorbed. So in this case, energy is released. So it means that the binding energy of daughter nuclei is greater than binding energy of Z. And individual particles like neutrons, they do not have binding energy. As I said before, that individual particles, they do not have binding energy, means no binding energy is associated with individual particles, because those individual particles, they are not in the nucleus, so there is no binding energy associated with individual particles. In this case, there is no binding energy associated with these two neutrons, and also no binding energy associated with this neutron. So how we can calculate energy released? At A2 level, you need to understand two methods to calculate energy released. One method, so I will be writing here method 1, simply is if you need to calculate energy released, this is based on mass. So simply you need to find out the mass difference and you need to multiply with c square, so you can find out the energy released. But when you calculate this mass difference, you have to consider mass of individual particles as well. So total mass on the left side minus total mass on the right side. So you will find delta M. And the second way to calculate energy released is, so the second method, energy released, simply we can calculate by calculating the difference between binding energy on both sides. So energy released will be equal to the total binding energy. Let me write on here, total binding energy of products means daughter nuclei, so we can say total binding energy of daughter nuclei. These points are very important, so you need to listen them carefully and you need to understand. You don't need to watch a lot of videos, but the video you watch, that video must make sense to you. So that's the main point. So listen carefully and try to understand what I'm explaining you now. This is very important for A2 physics, especially for nuclear physics. Total binding energy of daughter nuclei minus total binding energy, total BE of parent nuclei or parent nucleus. So we can say parent nuclei or parent nucleus. So in this case, we have these two daughter, so these are our daughter nuclei, so these are daughter nuclei, and this is our parent nucleus. So the binding energy of these two we have, this is binding energy of one nucleus, this is binding energy of another nucleus. So simply we will write on here 1.25 plus we have 1.81, and both of them they multiply with 10 to minus 10 minus binding energy of C. So here we have binding energy of C, so we need to find out binding energy of C. But we have the energy released, so this is the energy released. Physics is beautiful, so try to understand. When these things they will make sense to you, you will love physics. So try to understand. Physics is way of thinking, so develop your way of thinking. So binding energy released we have already, so we can write on here, this is 2.94 times 10 to minus 11. So we can find out binding energy of C. So if we solve this one, we will get binding energy of C. So in this case, binding energy of C, if we do these calculations, we will get 2.77 times 10 to minus 10 joule. So this is binding energy of Z nucleus. So we can say binding energy of Z nucleus. So this is binding energy of one Z nucleus. So simply we can write on here 2.77 times 10 to minus 10. This is in joules. So if we solve this one, our answer will be in joules. But we want answer in mega electron volts. So we have to divide this one by 1.60 times 10 to minus 13. Now if we solve, your answer will be in mega electron volts. And your final answer will be 7.43 mega electron volts. So this is our final answer. And this is how you need to answer. So these two methods, please, are very important. I hope you have better understanding. If you're not clear, so look at this one. So energy released is equal to mass difference. You have to include mass of individual particle in your calculation. Mass of individual particles you have to include, you have to consider. But here when you use when you find energy release based on binding energy, you no need to consider binding energy of individual particles, because individual particles there is no any associated binding energy with individual particles. So that is the main concept. I hope this question makes sense to you, and if these videos are helping you to improve your understanding of physics and they are also helping you to understand these questions better, please like and subscribe, because your encouragement is very important to make more videos. And if you're looking for more resources, you can also join Patreon, and also by joining Patreon you can also support this work. Question 10 says ultrasound and X-rays are types of wave that are used in medical diagnosis to form images of internal body structures. Complete table 10.1 to state for each type of wave the method of production of the wave, whether the wave that is detected and used to form the image is the wave that has been absorbed, reflected, or transmitted by the internal body structure. So first thing, method of production, ultrasound waves. How do we produce ultrasound wave? Just by vibrating quartz crystal. So simply we can say vibrating quartz crystal. So we can write on here vibrating quartz crystal. Quartz crystal. So quartz crystal, or simply you can say quartz crystal. How do we produce X-rays? When accelerated electrons are decelerated, we produce X-rays. Or simply you can say when accelerated electrons hit the metal target, we can produce X-rays. Detection means detected wave. In ultrasound, simply we have here, this is transducer, and here we have boundary between two different media. We will send ultrasound waves, and when they will reflect from this one, this reflected wave will be detected. So this reflected wave will be detected, and with the help of this one we can form ultrasound image. So simply we have to say here reflected wave is detected. And in case of X-rays, so here we have source of X-rays, we can say this is source of X-rays, and here we have the body, and at the end of this one here we have photographic plate. So this one is the plate, photographic plate. We will see the image on this one, and this is image on this plate is formed by transmitted wave, means waves will pass through this one and they will form the image here, transmitted. So simply you have to say transmitted wave. So detected wave is transmitted wave, means the X-rays that pass through the body of the patient. So this is how you can answer this question. Part B1 says for one type of wave passing through tissue, the wave has 72% of its initial intensity after it has passed through 6.2 centimeters of the tissue. Calculate the linear attenuation coefficient of the tissue for this wave. So the best way to answer this question is, first of all, we can simply imagine this one is the tissue and the thickness of the tissue is given to us. So this is thickness of the tissue. Value of X is equal to 6.2 centimeters. Initial intensity, imagine that this is I naught. So the transmitted intensity in this case will be equal to 0.72 times I naught, and we need to calculate value of mu. So value of mu for the tissue we need to calculate. So simply we have to use IT, transmitted intensity. This one has to be equal to I naught e to the power of negative mu x, because intensity will decrease exponentially. So this is the point. So it will decrease exponentially. So we have to use this formula. IT we have, that is equal to 0.72 times I naught, and here we have I naught e to the power of negative mu x. So I naught we can cancel, so we left with 0.72. this is equal to e to the power of negative mu x. Now if we take natural log on both sides, we can say ln of 0.72. this will be equal to ln e to the power of negative mu x. Ln e is equal to 1, so we can write on here ln of 0.72. This is simply equal to negative mu x. So we need to find out value of mu, so mu will be equal to negative ln of 0.72 divided by x, and value of x we have, that is equal to 6.2 centimeters. Now if we solve this one, we will get 0.053 per centimeter. So this is the final answer. This is how you can calculate. Is a typical question. So this is how you can calculate. I hope this makes sense to you. You have to be very careful with this unit. As this unit is centimeter, so we got per centimeter. If this unit was meter, we will get per meter. Second part says another wave of the same type as in B1 passes through 9.3 centimeters of the same tissue. As tissue is the same, it means that value of mu is equal to 0.053 per centimeter. So this is the value of mu. We need to calculate the percentage of the initial intensity of the wave that is attenuated. Attenuated means that absorbed. So absorbed by the tissue. And we need to understand initial intensity. This one has to be equal to the intensity absorbed, or you can say attenuated, plus intensity transmitted. So this is the main idea. So if you need to find I absorbed, so we can say I absorbed, this will be equal to I naught minus IT. So this is our main idea, main concept. So how we can calculate IT? So first of all, we can draw, this is our tissue, and the thickness of the tissue is given to us. Thickness of this one is 9.3 centimeters. So this is value of x. So we can say this is intensity of incident wave I naught, and the intensity of transmitted wave, let's say this is IT. So we can simply write on in this case IT, this one has to be equal to I naught e to the power of negative mu x. So we can write down IT by I naught, so we can find out the fraction of initial intensity that has been transmitted. So we can find out IT over I naught, and this is equal to e to the power of negative mu x. We have value of mu, that is 0.053, and value of x is also in centimeters, so you can use this one here, 9.3. E to the power has no unit. If you have e to the power of something, it has no unit. So this is the main concept. So if we solve this one, we will get in this case IT over I naught, that will be equal to 0.61. So it simply means that IT, from here we can say IT is equal to 0.61 of I naught. So this is IT is equal to 0.61 of I naught. So how about I absorb? So you can find out from here. So we have I naught minus we have 0.61 I naught. So from here we will get, this will be 39, means 0.39. So this is 0.39 I naught. So this is I absorb, means I attenuated, I absorb. So you got this one here. Question was asking you how much it is absorbed. So we got I absorb is equal to 0.39 of I naught. We need to convert this one into percentage. So simply we have to multiply this one by 100. So we can say percentage attenuated. So we can say percentage attenuated. So I absorb in percentage. So simply we can say percentage attenuated. So we can say percentage attenuated. This one has to be equal to 0.39 multiplied by 100. So this will be equal to 39% of I naught. 39% of I naught. You can also do this one in a little bit different way. So let me explain you that one. So here we can write down the percentage attenuated in a little bit different way. We can say percentage attenuated. This one has to be equal to 1.0 minus we have 0.61, means this value 0.61. So this is, and you can multiply this one with 100, so you will get here 39%. So this is how you can calculate. So this number is telling us 61% passes through the tissue and 39% is absorbed by the tissue. So this is how you can answer this question. I hope this question make better sense. And if you have any questions, please leave your questions in comments and I will try to answer as soon as possible. And if you're looking for extra resources, you can also join Patreon. On Patreon, you will find more resources. See you next video.